This is FE Peer Review, the Flat Earth Peer Review channel. The date is June 20th, 2020. The video in review is titled Flat Earth, Flywheel Engineers Know Earth Could Not Withstand a 1,000 mile per hour rim velocity, dated June 17th, 2020. The video is by Daniel Pratt 2. No, excuse me, just Daniel Pratt. Mr. Pratt, for brevity, I will sum up your hypothesis as I understand it. Viewers of this video are encouraged to watch Mr. Pratt's video for his full explanation. Mr. Pratt shows that the rim velocities of two angle grinders are far less than the rim velocity of Earth at the equator. To operate the grinder at higher RPMs and therefore increase the rim velocity would result in the destruction of the grinder blades. He then points out that the Earth apparently resists a far higher rim velocity, and despite it not being made of steel like the grinders, it does not fly to pieces. So he concludes that the Earth is not rotating. It is not my intention here to do the math required to explain Mr. Pratt's errors and to fix them. It is my intention only to point out how Mr. Pratt's basic assumption is wrong. It is for Mr. Pratt to fix the errors in his observation and conclusion. Mr. Pratt fails to demonstrate that the rim velocity is in fact the cause of the stresses resulting in the destruction of the grinder blades. For example, take the angle grinder blade and propel it forward at 1,000 miles per hour and it would not come apart in midair. Propel it forward at twice that speed and it still would not, but rotate it around an axis so that the direction of that velocity is no longer a straight line and it will indeed break apart. Recall that force is directly related to acceleration. Force equals mass times acceleration. An object moving at a constant speed, a velocity, is experiencing zero acceleration and therefore zero force. A rim velocity, as Pratt shows it, is by definition a constant speed.
Here we are at an RPM 2 miles per hour calculator.
The solution that he is seeking is given in miles per hour. That is a velocity, a constant speed, not an acceleration. Now I will bring us to this page here. Links for all of these pages will be found in the description, by the way. This page on centripetal force is very useful for our discussion. The cause of the stresses that tear apart the grinder blade is the centrifugal force, which has two components. One tangent to the rim, that would be, imagine that this is our grinder blade, and this is the rim of the grinder blade, and that's a point on the rim. So, two components, one tangent to the rim, that would be this horizontal line, and the other is perpendicular, which would be back towards the center of the blade, or as you can see here, this portion. The tangent component is simply the rim velocity, that's this piece, and does not induce a stress in the grinder blade itself. The source of the stress is the perpendicular component, this direction, that is pulling the blade edge back towards the center of rotation. As the blade spins, the angular change causes a radial tensile force in the blade, which eventually exceeds the material strength and the blade flies apart. Let's take a look here at this picture of a grinder blade. Here's our blade. It's held at the center by the grinder and the nut at the grinder center. Now imagine that there's this point of material here out on the edge. And this point, this grinder blade is rotating, and this point of material, if it were free to move on its own, would simply, let's say our grinder blade is rotating clockwise. That material would simply continue off to the right. However, that material is not free to move on its own. It's molecularly bonded. It's tied to all the material all the way to the center of the blade. So as that piece of material tries to fly off to the right, it's being pulled back towards the center of the blade by the material that it's touching, that it's connected to, that it's bonded to. And that material is bonded to the next and to the next and to the next, all the way to the center of the blade. So when this material at the edge of the blade tries to go off in a straight line to the right, it's pulled back in towards the center. Forces being equal and opposite, it's the same as saying that it is pulling out away from the center. So it's inducing, there's a tension force trying to increase the radius of this blade. Another way to think of it is to imagine that instead of a blade, we are looking at a giant pizza dough. And the guy's back there in the pizza kitchen flipping that dough in a big circle. And as he tosses that dough up into the air and spins it, it gets wider and becomes a bigger circle. That's what this blade would like to do if it was that flexible a material. So there are two ways to increase the perpendicular component, the component that's causing the stress. One is to increase the radius while maintaining the same angular velocity. We can increase the radius, make this circle bigger. And if we do that, maintaining the same angular velocity, it would be like this line, or up here, comes out to here and comes down. The second is to keep the same radius, so we're keeping the same radius, and increase the angular velocity. So now instead of going from here to here in, for example, 1 second, it goes from here all the way over to here in 1 second. So there's much more pulling happening. Mr. Pratt needs to analyze his observation taking into account the angular velocity, which is the radial stress inducing component. I recommend the following web pages as a primer for the concepts and math involved in carrying out a proper analysis. Wikipedia's web page on centrifugal force is a good starting point. Also, the web page on angular velocity. In fact, I suggest, Mr. Pratt, that you read that first and then return to the centrifugal force page. This page, physicstasks.eu, is also a very useful page, and it contains specifically the solution to what is the centrifugal force at the equator. How much does it affect, how much does it counteract the force of gravity? And then finally, this page that we looked at a little bit already, Lockhaven EDU. All the links are in the description. Thank you. If you found this video useful, please subscribe, please like, and feel free to share. Have a great day. Bye.